Okay, can you see this screen? Okay. So this is so I'm not sure. I hope I will be able to present because this is uh, slightly older laptop and it might stop working in between. So let us do it till we are able to get it. So I've written down some, I mean I've pasted some of the formulas here, and we will try to uh, get them. So the idea is that we are now trying to look at something called ideal Fermi gas. Ideal Fermi gas. Basically, that is ideal gas of fermions. And these systems are supposed to be treated using something called Fermi Dirac statistics. Okay. We had seen earlier that when we talked about general quantum statistics, the grand canonical partition function, grand canonical partition function for Fermi Dirac statistics is given by this Q of Z, the fugacity, V, and of course beta, the temperature, inverse temperature, is equal to product over all the single particle energy levels, epsilon, and 1 plus Z e to the power minus beta epsilon. So the product of all these terms will be the grand canonical partition function, where the fugacity is given by e to the power beta mu. So this is our fugacity, and the next expression that we had was with respect to the average number of particles. Okay, so the average number of particles n is given by, you can obtain this by this expression, that partial derivative of logarithm of grand canonical partition function with respect to z. And if you do this, you will get this as sum over the single particle energies and 1 by z inverse e to the power beta epsilon plus 1. Okay, so this is your single particle energy states, and then we have written this as sum over epsilon, n epsilon, where n epsilon is the, so n epsilon average, which is given by 1 by, I can write this in the following fashion, beta minus, just a minute, Hello, can you hear?
Yes, sir.
Hello, am I audible? Okay. And is the screen also visible? Okay. So this you can write it as e to the power beta epsilon minus mu plus 1, and this is the average occupancy of a single particle energy level. Okay. And we had seen earlier that this also can be written as the probability of occupation of energy level with energy epsilon. Okay, and if you look at this expression is suppose if you are looking at this expression, that is examine this. Examine this at T equal to 0 Kelvin. This is the lowest temperature that you can expect to think of. And if you look at this, this implies beta is going to infinity. Okay, beta is infinity. So now if you look at this expression, if beta is infinity and if epsilon is less than mu, then it will be e to the minus beta infinity. That means this factor will become 0. Okay, so uh, this n epsilon will go to 1 if epsilon is less than mu, and n of epsilon, this n epsilon will go to 0 if epsilon is greater than mu. And of course this is true in this limit. Okay, so in this limit. So at t equal to 0, this is what you can expect. So we can define the chemical potential at 0 Kelvin as Fermi energy, and denote it as some epsilon. So I can say that since we are talking about 0 Kelvin, I can explicitly say that this mu is Fermi energy. And you can plot, that is in terms of energy and then the occupation n epsilon. And let's say you have somewhere here your epsilon F, the Fermi energy. So this is going to be 1 up to that Fermi energy, and then after that it is 0. That means it is just like a step. It is 1 up to this and 0 after this. And this is 1. So this is what it is. Now you can see what happens if you have slightly higher temperature. Now you can see that even if it is a higher temperature, the expression suggests that there is not much going to change in this region. In the worst case, for some temperatures of our interest, you can expect that there will be a change in the vicinity of this. That means it is almost same up to this. It is 1. Okay, and in the vicinity of this there can be some change, and then it will remain 0 in this. So there is going to be some small region, okay, which I may just represent like this, around which there will be some change. Okay, so n epsilon changes appreciably from its T equal to 0 Kelvin version only in a small region around epsilon. Okay, when I say changes for T greater than 0, appreciably from its T equal to 0 version only in a small region around this epsilon. Now this change also, that you can say that this change happens because of the Pauli principle, because Pauli principle will not allow particles to. What does Pauli principle tell you? That so essentially the way the situation is something like this. Suppose you have a collection of electrons, and then imagine that you have got these energy levels. So let's say you have these energy levels, okay, and I am assuming that all degrees of freedom are being taken into account. There are infinitely many levels, and you can have one particle in each one of this. So you can have a particle here, particle here, particle here, okay, and of course there can be some degeneracy, because if there is some spin, then you can have 2 particles in this levels. But let's assume that we consider all the degrees of freedom, and then in such a way that if you have n number of particles, then there is a particular energy level above which all are empty. Okay, so there is a particular energy, and this energy is your epsilon. So this is, since this is also interpreted as a probability, probability is 1, means up to epsilon f all are occupied, and above this epsilon f these are empty. This means the probability of occupation is 0 at above this. So this is T is equal to 0 Kelvin scenario. This is what happens at T equal to 0 Kelvin. Now what happens at finite temperature? Suppose if you increase the temperature T greater than 0 Kelvin. Now what happens? Each one of this particle will acquire some thermal energy, correct? So each particle acquires thermal energy okay, which is of the order of kb times t. Okay, that is your thermal energy that each particle will acquire. Now suppose you look at this particle and it acquires some thermal energy. Okay, so let's say that thermal energy can take it to third level, but then it cannot go to third level because third level is already occupied and Pauli will not allow this third level to be occupied again. So all these particles which are deep seated will not be able to use their thermal energy because they will not be able to occupy any other level within that kT. So essentially that will have no impact on this energy level structure. What happens to these particles which are occupying the highest and slightly near the highest level? Now this the one which is at epsilon f can go to the next excited state because there are states are there, empty states are there. So now what happens because of this reason, you will see that these particles which are in epsilon f can get promoted to higher level. So this can get promoted to next level. This can get promoted to next level. So there is going to be only some energy levels close to the Fermi energy will participate in excitation process. Okay, so uh, so what we have is only those particles uh, close to Fermi. Hello, any question? Close to Fermi level participate in excitation. Excitation. Others will have no effect on this, and that is the reason why only some of the levels which are very close to this epsilon f will have their probability reducing, and some of the levels which are just above the Fermi level will have a non-zero probability. Okay, so whatever the probability that is lost here will be gained here because these particles will occupy this level. So this is essentially the mechanism how the thermal energy is used. Now you can see that there is one can make an estimate of how this thermal energy how much thermal energy you should have. So one can so we have one energy. So this epsilon f is a characteristic energy. Now we can ask a question, what is the temperature associated with it? This one, that is epsilon f is actually can be written as kb times tf. Okay, if you write it like this, then we call this tf as Fermi temperature. Okay, we call this as Fermi temperature. Okay, so let's try to get some idea of what this Fermi temperature is. Typically, I do not know if you have some idea from your solid state physics. Typically, the Fermi energy of a metal is of the order of 5 to 10 electron volts. Okay, let's take typically. For a metal. Okay, I have written typically 2 times. So typically this is of this order. So if this is of this order, then you can say that so your Fermi temperature is epsilon f by kBt. So that is you have 10, and 1 electron volt is like 1.6 into 10 to the minus 19 joules divided by 1.38 into 10 to the minus 23 joules per Kelvin. So this is roughly the order of magnitude. So you can see that this is 16 by 1.4 roughly. So 16, that is like 16 by 1.4 into this is 10 to the 4 Kelvin. Okay, so 16 by 2 is 8, so 16 by 1.4 is more than 8. So let's say that this is 10. Okay, so this will be of the order of 10 to the 5 Kelvin. Okay, so 10 to the 5 is like 1 lakh Kelvin. Okay, 100,000 Kelvin. Okay, that's the kind of temperature, which is very huge temperature, right? So, what this temperature means is that this temperature tells you that if you want, if we want all particles to get excited. If we want all particles to get excited, that is even the particle in the ground state, okay, then we have to increase the temperature to Tf. If you want all particles to be excited, we have to heat up the temperature Tf. Then you can say that every level will have, so typically, suppose if I plot this graph, what happens to this graph at temperature Tf, let's say. Suppose you want to ask a question, what happens to this graph at Tf? So this will be something like this. So it will be like this. That is, every probability will be less than 1, and every probability outside will be also greater than 0. Okay, so this is probably how it looks like at T is equal to Tf. Now you can understand that if your temperature is less than Tf, then this is not going to be the scenario. Some particles will not get excited. Some deep-seated low-energy states will remain. The particle occupation will remain 1. Now, suppose if you are working. Suppose we want to work with. Suppose we work with metals for their electronic properties. okay, such as electrical conductivity. Or thermal conductivity. Electrical conductivity is it is the stimulus is the applied electric field or the potential difference. Thermal conductivity is stimulus is the temperature gradient. In both cases, electrons will move, giving rise to conduction. And we would like to understand how this conduction will take place and electronic specific heat, etc. Uh, we work with metals for their electronic properties, mainly at room temperature. Of course, we also try to study as a function of temperature. Okay, we do it as a function of temperature, but mainly we work at room temperature. And room temperature is that is our temperature of interest is roughly 300 Kelvin. Okay, so now if you look at that is if you just look at the order of magnitude, this is like 10 power 2 Kelvin. Now if you look at T divided by TF, is of the order of 10 to the minus 3. Okay, so this is supposed to be very small. So typically, if we have T by Tf of the order of 10 to the minus 2 to 10 to the minus 3, if this order, then ideal gas, ideal Fermi gas deviates from its T equal to 0 Kelvin behavior only slightly. Okay, which implies so this implies that we study, so we understand T equal to 0 Kelvin case and add high temperature corrections to physical properties or thermodynamic properties for that matter. Okay, so that is the practical aspect, because since we don't have too much of departure from T equal to 0 case, so we should understand T equal to 0 case, and once we understand T equal to 0 case, then we can get the high temperature properties by adding progressively corrections to T equal to 0 case. Okay, so I'm trying to make a point that study of T equal to 0 Kelvin case of ideal Fermi gas is important because its results are relevant even in high temperature situations where the temperature, because Fermi temperatures are very large. For all reasonable temperatures of our interest, T by Tf will be of the order of 10 to the minus 2 to 10 to the minus 3. And hence, large amount of results that we study at 0 Kelvin will be still valid and useful. And the behavior will not change much. It only changes slightly. And that slight change in the behavior can be obtained by means of what are called perturbative corrections. Okay, so we can do that. So it is important that we study t equal to 0 case explicitly. Okay, so now to study this one, we have. So let us say that since this is an ideal Fermi gas, this ideal is important. That means you have each of the particle is what is called a free particle. So the energy for the free particle is p square by 2m. Okay, and the density of states. Actually, the expression that I have written down earlier is itself valid. Okay, but let me write it in the following fashion. Density of states is given by you have 4 pi p square into dp over d epsilon into d epsilon. That is in your p space. Okay, so you have a p space and you have a sphere of radius p, and there is another sphere of radius p plus dp, and the volume of this annular region is given by 4 pi p square dp. Okay, and let's say that this entire thing is in some volume V. Okay, so we can say that there is a volume associated with that, and then I want them to be discrete, so I divide this by h cube. Okay, this will be the phase space volume associated with this, and this is h cube. Okay, so this is basically I'm writing A of epsilon into D of epsilon. This is the number dn. Okay, the number of cells of h cube is its minimum dimension, and this is how we can write this one. And of course, we must also write down some factor g, and this g is essentially a multiplicity due to spin. We are talking about fermions, so they are half integral spins. Okay, so if S is the spin, it can be spin half or spin 3 by 2, etc. If S is the spin, then your degeneracy is going to be 2 times S plus 1. So if it is S equal to half, then you have 2 here. So this tells you that you have an expression for your A of epsilon. So you know that this p square can be written as twice m into E, and P is equal to square root of twice ME. So dP over d epsilon is square root of twice m into 1 by 2 root E. Okay. So now you can see that this is going to be, so I can now write down my A epsilon to be G V 4 pi p 4 pi into twice ME into square root of twice m by 2 into 1 by root E. Okay, so this 2 will cancel. Let's say I have 2 here, and there is m, so there is 2. So this is going to be equal to GV into 4 pi. So this is 1 minus half is root, so root 2m into, of course, there is an m sitting outside, into square root of. So this is the kind of expression that we have. That root key part, as you can see, is obtained. Okay, so in case if you have this g to be 2, okay, then you can write this as v into 4 pi into 2m to the power 3 by 2 into square root of. Of course, there is this h cube sitting here always. There is the h cube, and then h cube. Okay, so if you want to get back to your expression that we have written down in the case of Bose-Einstein, we of course used a different, we used the case space there, but then you write down your h as 2 pi times h cross. Okay, so in that case you will have your A epsilon to be V into 4 pi twice m to the power 3 by 2 into square root of E divided by twice pi the whole cube into h cross cube. So twice pi the whole cube is, you can write down as 8 pi cube. Okay, so that is V 4 pi, and I can write this as twice m by h bar square to the power 3 by 2, and this divided by 8 pi cube into square root of. Okay, so that is equal to, you have V divided by 2 pi cube, sorry, V divided by 2 pi square into twice m by h bar square to the power 3 by 2 into root 2. So I think this is just to make a connection with what we have seen earlier. Okay. And now once you know this, you can write it in the following fashion. So our starting point is that we have this density of states, A of epsilon, which is called density of states. Because you remember why we were interested in density of states. So the density of states is to convert a summation into an integration. So the density of states here is given by V into R4 pi V okay, into twice m by h bar square by h square to the power 3 by 2 into root of epsilon. Okay, so now what we have to do, so let's say that we simple. Suppose if I want to know how many particles are there. Okay, so if the total number of particles are uh, given by the total number of energy levels, because I have only those many particles. Correct. Each particle can be existing only in one level. Right. So you can say that your average number of particles, your n, can be written as integral from 0 to this epsilon f and a of epsilon into d epsilon. That is, you integrate this density of states from 0 to epsilon, you will get total n. Okay, this is for 0 Kelvin. Now this will be slightly changed if you are taking high temperature. So what happens at T greater than 0 Kelvin is that now you are in principle all energy levels up to infinite energy are available. So you should get this n from 0 to infinity, you have to integrate, and of course d epsilon, a of epsilon. But now depending on what is the temperature, there is a probability for the hello. I was out of meeting for some reason. Can you hear me?
Yes, sir.
Okay. So, so the point is that this each of the energy level will have certain probability. So we have to write down the probability of that energy E and then integrate this. Now, what is this probability of energy E? Probability of this energy E is average occupancy. That's what we have already seen. So this is how you have to calculate your average number of particles. Now, on the other hand, suppose you are interested in finding out what is the energy of the system. Let's say we are interested in internal energy. U, which is essentially the average energy. How do you get the average energy? In 0 temperature case, up to epsilon f, you have probability of occupation to be 1. So you have T epsilon, A of epsilon into epsilon. That's all. So that is what gives you the what is called the average energy. What will you do at T greater than 0? Very simple. So you write U as integral 0 to infinity d epsilon, A of epsilon, epsilon and P of epsilon, which is essentially same as average number of particles occupying a single particle energy levels. And once you get U, then you can write down your CV as dou u dou t, and other properties you can obtain from this. So this is the scheme of getting zero temperature results. What happened? Any problem?
Sir, we lost the presentation right now.
That's the presentation. Okay, it looks like my connection is lost. Could you see it now?
Yes, sir, it is visible now.
Okay, so this is the scheme where you will, I hope you have just lost the connection, but just to say, these are the expressions, whatever I have written on the left hand side for T equal to 0 Kelvin. Okay, and these expressions for finite temperature, that means for non-zero temperatures, will be like this, except that two changes. One is the upper limit is going to be infinity, whereas here upper limit is epsilon f. Okay, that is one change. And second thing is, since each of the energy level is has certain probability, you have to multiply that with the probability. And this probability is essentially this average n, which is given by 1 by z inverse e to the beta epsilon plus 1. So that is what you have to do that. Okay, so this is something which one can do, and doing this part is simple because here you don't have that probability, and this is because these equations will reduce to these equations because your p of epsilon is a step function. So p of epsilon is 1 if epsilon is less than epsilon f, less than or equal to epsilon f, and 0 if epsilon is greater than epsilon f. And what is this? This is the statement of probability at t equal to 0 Kelvin. So if you have these expressions and then substitute this probability distribution, you will get this, whatever I have written on the left hand side. Okay, so it is simple to do this one. So I can now write down okay. So if I write down that just give me a minute. So we see that as a function of n, we will be now able to obtain what is called okay. I think I have to keep this. To use one of these expressions. So let me say that twice n Okay, so finally I have written this in the following fashion. So this is the expression I think I should probably use it finally, because this seems to be correct, and of course this is true for g is equal to 2. Hopefully we haven't. So if I use this, then let us try to get our n. So n is equal to 4 pi v into twice m by h square. Because we are used to writing h cross, maybe I will just put that in h cross language. That is, you get twice m by h bar square into v by 2 pi square, right? So that is, so let's write that. V by 2 pi square into twice m by h bar square to the power 3 by 2 into root e. And of course, this is the energy part, and integrate this from 0 to e d epsilon. So that is given by v by 2 pi square and twice m by h bar square to the power 3 by 2 into epsilon f to the power 3 by 2. By pi 3 by 2, that is 2 by 3. Okay, so now what you have is this implies I will have epsilon f now can be written as r epsilon f to the power 3 by 2, let me put it. So this 2 will cancel with this 2, and then I have 3 pi square into n by v, 3 pi square n by v into h bar square by 2m to the power 3 by 2. So this will give us an expression for the Fermi energy in terms of the number density. So epsilon f is given by h bar square by 2m into 3 pi square n to the power 2 by 3. where the small n that I am writing here is basically capital N divided by V. This is the number density. So note here that epsilon f scales like the number density to the power 2 by 3. Epsilon f behaves has a behavior with respect to number density. So once you give me your number density of fermions, I will be able to find out what is the Fermi energy, or vice versa. If you give me Fermi energy, I will be able to find out the number density. So sometimes you will have simple problems of this type asked in the examination, that either what is the scaling of Fermi energy with the number, or give the Fermi energy and try to find out what is the number density. The second integral, which is also not very difficult, is the energy U, and energy U is equal to integral. So you have V by 2 pi square into twice m by h bar square to the power 3 by 2 into integral 0 to epsilon f. Because this is average energy, then I have to write down the energy first, that is energy, into, of course, the root energy of B. Now this is simple. So you have V by 2 pi square twice m by h bar square to the power 3 by 2 into 2 by 5 into epsilon f to the power 5 by 2. Okay, so now you can see that the expression for the energy is like this, but then you have an expression like this. Okay, so let's say that I have an expression like this, and I substitute it here. So I can write this as V by 2 pi square into twice m by h bar square to the power 3 by 2 into 2 by 5. So I will take that 5 and then write this here into, let me say I have epsilon f and epsilon f to the power 3 by 2. And then substitute for this epsilon f power 3 by 2 from here. Okay, so then I have V divided by 5 pi square twice m by h bar square to the power 3 by 2 epsilon f into, I have 3 pi square n over V into h bar square by twice m to the power 3 by 2. So you can see this factor will cancel with this factor, pi square will get cancelled away, V will get cancelled away. So I have 3 by 5 n into epsilon. So this is an interesting result. That means if you are asking a question that if you have, okay, so if you have internal energy per particle, okay, so this is what you call as energy per fermion. Okay, so this is a fraction of the Fermi energy. You can show that this is 3 by 5 into epsilon f. 3 by 5 is 60.6. Okay, 60% of the Fermi energy. So energy per fermion is 0.6 times epsilon. Okay, so this is slightly more than half of epsilon. Okay, so this is result that you have from this. Now you can also ask what is the Fermi pressure. Okay, I'm more interested in Fermi pressure because so we will try to calculate Fermi pressure or pressure of ideal Fermi gas at t equal to 0. Now, how do we do this? This is something that you can get it by using this relation. That is PV by KT. PV by kdT is given by logarithm of Q. Correct? So, now logarithm of Q is essentially, it is sum over your single particle levels and then logarithm of 1 plus z e to the minus beta epsilon. Or in other words, you can write it as integral over 0 to infinity d epsilon a epsilon into, because this summation can be converted into integration by this factor. Okay, so let's try to do this. Okay, I don't want to do this integration up to EF because I know this probability is 1 below epsilon f and 0 after that, but we have to get this expression something like that probability expression. So for that, what I will do is I will try to do an integration by parts. Okay, so let me write this first. So I have 4 pi v. Sorry, so let me write down this one. V by 2 pi square into twice m by h bar square to the power 3 by 2 into integral 0 to infinity d epsilon epsilon to the power half into logarithm of 1 plus z e to the minus beta epsilon. Okay, so now let's try to do an integration by parts. So I consider this as my u and this as my dv. Okay, so then when I do integration, so I get du is equal to 1 by 1 plus z into e to the minus beta epsilon into z into e to the minus beta epsilon, okay, into minus epsilon d epsilon, sorry, minus beta, correct? Because I am doing this differentiation with respect to epsilon, and that is equal to I can write down this yeah, so this is equal to minus beta z into e to the minus beta epsilon divided by 1 plus z into e to the minus beta epsilon d epsilon, and I can take this to the denominator and then take this z also to the denominator, so that I will have this to be minus beta divided by Z inverse e to the beta epsilon plus 1 into dx. So that is my du part, and dv is d epsilon into e to the power half. So v will be equal to e to the power 3 by 2 into 2 by 3. So this expression, if I do an integration by parts, I have v by 2 pi square and twice m by h bar square to the power 3 by 2 into u and v, that is minus beta, sorry, v is 2 by 3 into epsilon to the power 3 by 2, and you have logarithm of 1 plus z e to the minus beta epsilon. Okay, and then minus, I have this expression, so that is plus beta into integral 0 to infinity d epsilon, epsilon to the power, I have 2 by 3, of course, 2 beta by 3, and I have epsilon to the power v du, right? So epsilon to the power 3 by 2, and the epsilon divided by Z inverse e to the beta epsilon plus 1. Remember, this expression is like the probability. Okay, so now this one has to be evaluated from 0 to infinity, and then you have an expression for this. Okay, so now you can see that this particular expression, what happens if your energy is equal to Fermi energy. Okay, if your energy is equal to Fermi energy, then so let's look at what happens to this expression. Okay, so let's now say that we are now only interested in doing this for up to Fermi energy. Okay, so let's look at what happens to this. That is logarithm of 1 plus e to the power beta minus beta into epsilon, and z is e to the plus beta mu, right? So I have minus mu. Okay, so this is what it is, and for so that is equal to, this mu should be written as epsilon f for t equal to 0 Kelvin. And now I have to take this epsilon is equal to epsilon f, then this becomes 1, and this is log 2 epsilon f to the power 3 by 2 plus okay. So epsilon f to the power 3 by 2 well, I think it is not okay. The issue is something like this. Suppose you generally work with high temperature, that means as epsilon goes to infinity. Okay, whatever is your mu, this factor will become 0. Okay, so e to the minus beta epsilon will go to 0. That means your logarithm of 1 plus z into e to the minus beta epsilon will go to logarithm of 1, and hence that goes to 0. So this term will be 0. This will go to 0 as epsilon equal to 0. That is because of this term. Okay, so let me put it like this. So this will go to 0, and this term will go to 0 as epsilon goes to infinity. Okay, so this term will go to 0 as epsilon goes to infinity. And as a result, this term will not contribute to this integral. So we have only this term in general. Okay. So I can write this one as so P V by KT, PV by KT is equal to V by 2 pi square into twice m by h bar square to the power 3 by 2 into I have 2 by 3 into beta. Okay, 2 by 3 into beta into 0 to infinity. I have d epsilon and epsilon to the power 3 by 2 into 1 divided by z inverse is the beta epsilon plus 1. Now you can see that this beta will cancel with this kbt and this v will cancel. Okay, so I have and now suppose if I come to, because this is like the expression, this expression is like the probability, probability of epsilon. And now if I specialize to 0 Kelvin and then say this is equal to 1, then I will have the pressure that is equal to 1 by 2 pi square into twice m by h bar square to the power 3 by 2 into 2 by 5 into epsilon f to the power 5 by 2. Okay, so this is equal to 1 for epsilon less than or equal to epsilon f. If I use that one, 0 for epsilon greater than epsilon f. So if I use that, then I get this. But you can see that this is somewhat like your energy, because your energy is also is going like epsilon f to the power 5 by 2, right? So from here, if you can see that I can write down from here epsilon f to the power 5 by 2 is equal to 2 pi square u by v into h bar square by 2m to the power 3 by 2 into 5 by 2. Okay, so I can write it like this. And suppose if I go and substitute it in that expression. Okay, so suppose if I write it like this, P is equal to 1 by 2 pi square into twice m by h bar square to the power 3 by 2 into 2 by 5. Now I have 2 pi square u by v. Okay, so that is and then h bar square by 2m to the power 3 by 2. Okay, and perhaps I have disappeared, so I thought. Okay, so let's. This expression is 5 by 2. Okay, into 5 by 2. Okay, so you can see that 2 pi square will cancel, and this will cancel with this, and 2 by 5 will cancel with 5 by 2. So P is so I've missed some factors there. Okay, I think I didn't write this 2 by 3 here. Right? So this 2 by 3 is sitting there. So there is an additional 2 by 3. So this is correct. So now I have P is equal to 2 by 3 into U by V. Okay. So this is an expression which is we have seen in ideal gas also, and this is also valid for ideal Fermi gas. It is also valid for ideal Bose gas. Okay. So in general, I will leave this as an exercise for you to show that if you are assuming that your epsilon is proportional to some p to the power some s. Okay, this is the energy relation in some d dimensions. Okay, so in d dimensions, then you can fairly generally show that the pressure, this is momentum, okay, this is energy momentum relation. Pressure can be written as S divided by D into U by V. Okay, so I will leave it for you to try this. And so in that case, you can see that for electromagnetic waves, that is for photons, okay, this was first shown by Maxwell and later used by Boltzmann. For photons, the radiation pressure is 1 by 3 into U by V. You can recall when Boltzmann was trying to derive Stefan's law, he used this expression. And that is because the energy for the photons is C times P. So here S is equal to 1 and D is equal to 3. Okay. So many times some questions like this you can answer. Suppose you have energy is like P power 4 in 2 dimension, then how will the pressure and internal energy or energy density for that matter, U by V is called energy density, are defined as small u. So how that pressure of this particular system and the energy changes, energy are related, then you can use this general result. And not only that, you can see that since your pressure is equal to 2 by 3 into U by V. Okay, so that is, this implies your pressure is proportional to epsilon F to the power 5 by 2. Correct? Pressure is proportional to epsilon F to the power 5 by 2 because pressure is proportional to U and U is proportional to epsilon F. And also recall from our previous observation that the epsilon F is proportional to N to the power 2 by 3. So these two things together will leave you that P is proportional to N to the power 2 by 3 to the power 5 by 2. So that means the pressure scales like n to the power 5 by 3. Okay, so this is degenerate pressure. Now remember, n to the power 5 by 3 is 5 by 3 is more than 1. That means it is exponential in character. That means if your number density is increasing, okay, this number density is essentially number per unit volume. So if your number density is increasing, the Fermi pressure will increase exponentially. That means it will increase very fast. And this is one thing which we should understand, because in places where the number density is very high, like in all these astrophysical systems, where white dwarf star or neutron star, this kind of places, the number density is phenomenally high. So when it is very high, the Fermi pressure is so important and dominant of the electrons that it can actually withstand the gravitational pull of the mass and then keep these stars stable for billions of years. Okay, so in a live star like our sun, for example, the gravity is compensated by the thermonuclear fusion, okay, fusion reaction. The energy that is produced by hydrogen fusing to become helium is what withstands this gravitational pull. But once the hydrogen is completely used up and you have only a helium, and fusing of helium to become higher elements is energetically not that favorable, and hence you have the star is supposed to collapse under gravity. But at that point, we observe these white dwarf stars or neutron stars. They are very stable for billions of years. And where this stability comes from is because of this Fermi pressure that comes because of the degenerate Fermi gas of electrons in ionized helium atoms, and that is sufficient to withstand. So we will do that calculation explicitly, and so that is what I am trying to tell you. This 5 by 3 greater than 1 is very important, because as the number density increases, your Fermi pressure exponentially increases, and as a result, it can withstand even the huge gravitational pull that is as a result of. So something like mass of the order of sun or more than sun is confined into an object whose radius is of the order of Earth. So that is, you can imagine now what kind of density that it will have. So if the density is so high, then the pressures are phenomenally high that they can actually balance the enormous gravitational pull that the star experiences. Okay, so these are kind of zero temperature calculations. I thought I will come to this, but anyway, so we will see if I can. So just like what we did in Bose statistics case, we can define some functions called Fermi Dirac functions. Okay, so similar to G nu of Z in BE statistics. We define F nu of Z here as F nu of Z is equal to 1 over gamma nu into integral 0 to infinity dx x to the power nu minus 1 divided by Z inverse e to the x plus 1. Earlier we had minus 1 there. So this is an expression that we can define. These are called Fermi Dirac. and I will leave it for you to verify that we can show based on the same method that we have used at that time. We can show that this f nu of z is equal to z minus z square by 2 to the nu plus z cube by 3 to the nu minus z to the power 4 by 4 to the nu plus etc. Remember, in G nu we have all plus 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 plus, but here you have all plus minus plus minus plus minus. Of course, this can be definitely written for small z. Okay, so you can say that for small values of z, small z, this f nu of z will be like z for any nu. Okay, so you can show that if you have, so these two expressions that I have written down in the beginning, so you can show that this G is your degeneracy factor. Okay, so starting from PV by KT, PV by KBT is equal to logarithm of Q, and then writing this integral like what I have done and then doing integration by parts, you will be able to show this expression. And then starting from this equation, that is starting from n is equal to, you have this expression, that is integral 0 to infinity d epsilon a epsilon into n epsilon. So starting from this, you will be able to show this expression. And then more generally from these two, and you can show this general expression. So this general expression, even though I have shown here at 0 Kelvin, but this is in general true. This is valid for, so one can show in general. In general, we can show this result. And of course, this is an identity. Okay, so once you define this, n and u in terms of this identity, in terms of these Fermi functions, so we will be able to prove this identity. Prove this identity. Okay, and once you prove this identity, we will be able to show by taking the derivative of this one, the specific heat can be related to these Fermi functions in this fashion. So essentially, this entire exercise, I request you to do it. But what this entire exercise tells us that if we are able to evaluate f nu of z, okay, so if it is evaluated either exactly or approximately or computationally is evaluated, then properties are related to them. So the important aspect of our thing is that we have to learn to evaluate these functions. Okay, so this is with respect to relating them. So I want you to try. If you are not able to do it in the next class, I will show you. So what we will do in the next class is that we will try to go out of this comfort zone of zero temperature thing and go to finite temperature, and then we will see that it's not very easy to do those integrals, even though they look simple because of this Fermi Dirac function, and we have to find out certain approximations. So there is a very interesting approximation which Arnold Sommerfeld had used. It's called Sommerfeld expansion, and we will try to use that technique to find out what happens if you have a collection of electrons in metals, which are free electrons, but they don't satisfy like Maxwell-Boltzmann distribution, like what Lorentz and Drude had assumed in their Lorentz-Drude theory of classical theory of electron gas. But Sommerfeld had developed a quantum theory of electron gas by using Fermi Dirac distribution, and you will be surprised that this work was done in the same year in which Fermi Dirac distribution was discussed. So this is called Sommerfeld theory of free electron in metals. So we will try to apply this Fermi Dirac statistics to electrons in metals, and we can talk about different properties, but more important property that we will talk about is the specific heat of electrons, because classically electrons also are treated as particles with certain degrees of freedom, and so we expect the contribution to the specific heat of metal equally from atoms or ions as well as electrons. But most of the times when you do experiments, it appears as if electrons don't contribute any specific heat at all to the specific heat of metals. It means it is like electronic degrees of freedom are frozen once and for all. Okay, so this was very surprising because classically it could not be explained because equipartition theorem assumes that you should have equal contribution of energy to all the degrees of freedom. If you apply Fermi Dirac statistics, you will be able to show, because it is not able to take energy because these degrees of freedom are frozen, because all these electrons are frozen in their respective energy levels, and because of very interesting consequence of Pauli principle, they will not be able to take this thermal energy because there is no room for them to get excited. And when they did this experiment at very low temperatures, they realized that there is some behavior for the specific electrons which will vary linearly with the temperature. That is, at very low temperature, people found that specific heat will go like some gamma times T plus alpha times T cube. Okay, this is low temperature. Now this is something which you can understand because this is what is lattice specific heat, lattice contribution. Okay, we have discussed this in one of our earlier classes. So that is due to Debye theory, and this is electronic contribution. Okay, so we would like to understand how specific heat of electron gas goes like gamma T, or is proportional to T. So that will be our aim in applying Fermi Dirac statistics to electrons in metals. Okay, so I will stop here. If there are questions, we can discuss. Otherwise, we can. Any questions? Okay, so if there are no questions, then we can close. We will meet in the next class. Shruti, we will close.